This hypothesis testing consists of 6 steps, and last week we have done step 1, 2, and 3. Now, step 1 is where we put the claim, which is a statement that has exactly one truth value, either true or false. Now, in this chapter, we will deal with claims about the population mean with mu, with sigma known, population mean with sigma unknown, population proportion, and population variance. And then the claim may be explicit provided in the problem, otherwise need to be paraphrased. And then in step 2, from that claim, we develop 2 competing complementary hypotheses, denoted by null hypothesis and alternate hypothesis. And the hypothesis will be written using these braces here. Okay, we need to use the brace here. Okay, and then null hypothesis with colon, alternate hypothesis with colon, and then as for the inequality sign, null hypothesis will contain equal sign. The alternate hypothesis will not contain equal sign and should be the opposite of what we have in the null hypothesis. Okay, so you see, for example, if in the null hypothesis we use equal sign, then alternate hypothesis we use not equal. Okay, if no alternate hypothesis we use greater than, then null hypothesis we use less than with equal sign. Okay, now I think I said in the past that our textbook and more recent textbook always use equal sign in their null hypothesis. Okay, now they have their own reason though. They have their own reason. The reason they do that is because when they do their step 3, whatever they have in their null hypothesis, is the one they use for parameter. Okay, whatever they use for null hypothesis, that's what they use for their parameter. Now, we did some examples up to step 3 last week. Now, today we will continue with step 4, step 5, and then some examples again before we do step 6. Okay, so the setup is not that easy though. It's a big setup. But once we are good with this structure here, then we should be quite good when we do problems later on. Now, in step 4, it's supposed to be we will find the critical value from the traditional approach is we will find the critical value from the significance level provided in the question. Now, but because we use calculator already, we will not use this method. Okay, we will not use critical value method. Not for us now. Because in the past, if you look at my old tests and my old solutions, I still use critical value method, but I changed this since last year. Starting from last year, I enforced using TI-83-84, and actually to be more precise, TI-84, and we can now use p-value approach. Okay, now, this p-value approach is actually a more recent movement. Like recently, more and more people using p-value approach. In fact, in the last 5 years, there's a movement of people using what they call floating p-value method. But I will show you this later on. I will show you this later on after we're done with all this hypothesis testing with all the examples. Then I will say more about this p-value. Okay. Now, what is p-value? Now, p-value is obtained from test step 3. So in step 3, we get test statistic, right? In step 3, we get test statistic. Now, what is p-value? The p-value of this test statistic is the probability of obtaining the value of the test statistic or more extreme, assuming null hypothesis is true. Okay, so it is as if we say the following. It is as if we say the following. Suppose, let me put it here. Suppose my test statistic is here. Okay, C star is, let's say, 1.34. Now the p-value is the probability to obtain this test statistic or more extreme situation, assuming that the null hypothesis, the mu, is whatever we have in the null hypothesis. Okay. Now, of course, then we need to see the alternate hypothesis. We need to see the alternate hypothesis wants us to do it in left or right tail. Now, it depends on the this inequality sign here. Basically, you will see that if we see the parameter is less than a constant in the null hypothesis, then we will do what they call left tail. Okay, we will compute the area or the probability to have the left tail, and if it is greater than the constant, then we will do right tail. Okay, now in the null hypothesis, if we use not equal sign, then we will do two tail. So in case suppose on step 2, our alternate hypothesis have this notion here, has this inequality sign, then suppose this is our test statistic. Whatever the area I get here, I will multiply by 2. That will be the p-value. Okay, that will be the p-value. We'll go back there later on, don't worry. Okay, now how about informal conclusion? Informal conclusion is super simple. You only have 2 choices. The first choice, reject null hypothesis, if the p-value you get is less than the significance level. Other than that, we say fail to reject null hypothesis. Okay, now let's do example first, and then I will do one example, and then we come back here. Okay, in this step 4, step 5, so that you have a better feeling on what we have been doing. The thing is, like, we did the step 1, 2, 3 last week, right? So we may be a bit blurry right now. Okay, let's see, for example, this question 1. This question 1, a principal at a school claims that the average IQ score for students in his school is above 100. So that's the claim. Yeah, let me just do it right away. So step 1, claim. The claim is the average IQ score of students in the principal school is above 100. Step 2 on the hypothesis. The null hypothesis, alternate hypothesis. It's the average is above 100, so that's alternate hypothesis greater than 100, mu greater than 100. Okay, so the null hypothesis will be mu less than equals to 100. Okay, again, you may use mu equals to 100 if you like. Now, then from here you see that let me use blue color, that the claim is in the alternate hypothesis. Okay, and because it's greater than 100, then it will be a right tail. Okay, now this last part here is what we will use in step 4. Okay, this last part here, the statement that it is a right tail, which is actually not custom that we write it there. The blue color that I did, the blue writing that I did here is actually not a custom. So if you don't write that, you are fine. Okay, if you don't write that, you are fine. I would like to say that you have to write it, but it's one thing to say that's the right thing to do, that you have to do it. It's another thing that I say I suggest you to do it. Okay, now I'm teaching you a formal procedure right now, so I have to tell you that this is what you need to do, this is what you can do, so on and so forth. Okay, so the one in black color is the one you have to do. Step 3, test statistic. Test statistic, the C is 112.5. That's the sample average, right? That's the sample average. This is the claim. Okay, this is the sample size. This is the sample average. And then we have population standard deviation to be 15. Okay, so minus 100 here. Where I get this 100? I get it from here. That's where I get it from. Okay, then over the population standard deviation over square root of sample size. Now then when I use my calculator, I get a very big number, 5.27046. That's the test statistic. Okay, now then how about the p-value? How about the p-value? Give me a second. Give me more space. Okay. Step 4, test, p-value. Okay, what happened is the following. What happened is the following. This is what the curve should look like. Okay, now then the assumption, based on the assumption that the mu is 100, okay, the probability that the sample mean to be 112.5 or more extreme is what? Okay, that's what we want to find out. Well, that's the p-value. This is the p-value. What we have here is the area here is what we call the p-value. Okay, assuming the mean is actually 100. Okay, now we do right tail. Why do we call that right tail? Why we call that right tail? A little explanation. Why we do right tail here? Right tail p-value. Because of the following. Because of the following. Suppose the average is 100. Suppose the average is actually 100. And my sample mean is greater than 112.5, greater than 100, let's say somewhere here. Okay. Now, the thing is it possible? Is this possible? Is it possible that even when the mean, the actual mean is 100, we get a sample mean above 100? Is it possible? And the answer is yes. Okay, we may get a sample mean less than. Okay, we may get a sample mean greater than. Okay, now if it is possible, what is the probability? Now, so for us to say that 112.5 is greater than 100, okay, it is not enough for us to show that it is greater than in statistic, okay? We need to show that it is significantly greater than. Okay, to say, I have this little case yesterday. I have somebody who scored 80.5 in my test 3, in my other class, not this class, and somebody else gets 79.5 in her test 3. Now, can I say that the first person doing better than the second person? Can I say so? Well, of course, if you just look at the number, the answer is yes, the first person doing better. But is it something significantly better? Can I then claim that in big picture, the first person and the second person, the first person doing better than the second person? No, I will not say so. Why? Because even though number-wise the first person is doing better, but the number is so close that it could happen just by some coincidence. Okay, it is possible that it just happened that the second person forget a little detail, and I like to penalize points, right? Okay, so even though the first person score better than the second person in this case, the first person doing better, the number is better than the second person, I will not dare to say that the first person is doing better in general compared to the second person. No. In fact, if you look at their average, the second person still average much higher. Okay? So in other words, even though the first person is greater than the second person, okay, it is not significantly different. I mean, nobody in their right mind will ever say that, you know what, with this kind of score, I will marry the first person and not the second person. No, in no way. Because what? They're too close. They're too close. Okay, they're too close. You will not say you are richer than Thomas because you have $50,000 and Thomas have $49,990. You will not say that you are richer than me. Of course, I cannot say I'm richer than you while the evidence points otherwise, right? But to say that you are richer than me with that only $10 different, It's kind of like, come on, man, it's just another one. It's another one gas tank, simply because I fill up my gas and then I'm $10 less than you, right?
Excuse me, Thomas.
Uh-huh.
So in these two scenario, what does the difference need to be to claim that there's a significant amount of difference between the two?
Yes, that's what I'm going to. Now, if you see the difference is small, you will not claim that they are significantly different, right? Okay. Now, then, of course, when I increase the number, let's say the second person is 70.5 and the first person is 80.5, for example, then I start questioning myself. You know what? It could be different, right? Okay, but 79.5 and 80.5, no, that's too close. Come on, admit it, right? Even though in my final, when I provide you the grades, the first person, if this is the average, then the first person will get a B, and the second person, no, actually, both of them will get Bs in my grading, because my B is 79. Remember that? Okay, both of them will get the B. Now, but suppose the first person is average 80.5 and the second person is 78.5, then yes, the second person will get a C. But that's if you get the average for the class, right? Which includes test 1, test 2, test 3, test 4, and some quizzes and final. Okay, but I will not judge a student ability passing or not passing simply because of one test. No, it has to be from the average. Does it make sense? Okay. So at this point, if you don't do well in this class, I have that question a lot actually this last week. Thomas, should I keep the class or not? And I look at the grades. Yeah, I think you need to you need to drop the class. But Thomas, I only didn't do well in my test 3. My test 3 was 50. Okay. My test 3 was 50. Well, but the thing is your test 2 was 60 and your test 1 is 65, for example, right? So even though your test 3 is the worst one, none of your tests actually passing the class. So I have no reason to claim that you are supposed to pass the class while all your tests actually show otherwise. Does it make sense? Okay. Yeah, the average for this person is, if this is the number, then the average should be around 50 something, you know. Okay, now, of course, did I fail this student because that person get 50? No, not only that 50. I failed these students because of this and because of this, for example. Okay, I have the evidence of 3. But Thomas, what if I do, what if my test 4 is good? Well, first you need to define what is good, okay? For me as a teacher, what is good is the one that push your grade up to passing, okay? So what is good for that person, in my opinion, that person need to get 80 something, or maybe 85 something, okay? That's what is good, right? But at the same time, is it possible that person will get 85 or above, given that person scored these kind of scores in the first 3 tests? Okay, is it possible? Of course, possibility are always there, right? Just like as long as that has not happened, the possibility is there. Is it possible that the sun rise at the west tomorrow? Yes, it's possible. How possible is that? Near zero. Okay, near zero. Last year, nobody thought that the whole world will shut down like this, but it happens, right? 1 year after this. Okay, so it's still possible, you know, but how likely will that to happen? Come on, I will not bet my finger for that, right? Okay, so if that person asks me then, Thomas, is it possible for me to score more than 85 in my test 4? Yes, it's possible. How likely? Look at your conditional probability. If you get your test 1 65, 60, and 50 for your test 1, 2, 3, how likely it is that you suddenly score more than 85? Look at the average and look at the standard deviation, right? if your average is 50 something and your standard deviation is less than 10, okay, what is the chance that you suddenly score more than 3 standard deviation than your average right now? That's very unlikely, like very, very unlikely. The probability is actually less than 1%. Okay, is it possible? Yes, so less than 1% is still possible though. Okay, the probability that one person hit the jackpot of Powerball is very, very, very small, but it still happened. It still happened. Okay, it's just like I will not bet my finger on that. Okay, yeah, but at this point, of course, that person didn't drop the class, so that person asked me again, Thomas, do I have a chance? I say, regardless what's your chance right now, you have no way. You just keep on going, right? Why? Because you cannot drop the class anymore, right? Okay, for that person, and actually, because that person told me, Thomas, I think I will study a lot harder. I will give me the benefit of doubt. I said, if that's the case, yeah, just continue. Never wrong, never wrong. Okay, never wrong in that person's case. And then I actually say to her that even if you think you're gonna fail the class in this situation, I would like you to actually continue. Okay, continue studying for my pre-calculus class, because the next semester you will take pre-calculus class again, and hopefully by learning what you have here, when you retake it, your grade is much better. That's the way I actually encourage her. Okay, now, so coming back here, how do we know that this 112.5 is significant higher or not significant enough higher than 100? Now then, because the claim is the mu is greater than 100, right? That's the alternate hypothesis. So I need to come up with a sample. I need to come up with a sample mean that is significantly greater than 100, not simply slightly greater than. Okay. Now, of course, for that to happen, that we have a weakened significance, it has to be different enough. Like in this case, the difference may be not that big. It's only 12.5. Okay, but the fact that you can get 40 people getting that average, that means something. Okay, so it depends on how far it is from the mean. Also depends on the sample size. Okay, so maybe I put it this way. Suppose my sample mean is not that big. Suppose my sample mean is only 102.5. Now, of course, 102.5 is not big, right? But suppose on the top of that, you say that that's actually the sample mean I get from 4,000 people, for example. Now, then that tells some story, because with the size of 4,000 people, it will be so hard. To come up with a sample mean of 102.5, assuming the average is actually 100. Okay, so that's why we call that left tail, right tail, and that give us the procedure of how to compute the p-value. Okay, so the p-value is the probability. Again, the p-value is the probability to obtain that test statistic or more extreme case. Now, more extreme case in the sense that further from that sample mean, further from the parameter we claim in the null hypothesis. Okay, now, so what is the p-value here? How do we compute it? And notice that this is c-score, right? This is c-score. That's standard normal distribution. So the area there will be normal CDF 112.5. Actually, no, I'm sorry, not 100. We already get the c-score, the test statistic. So I get 5.27046 E9901. Now you will get the same value. If you use this normal CDF 112.5. 0.5, E 99, 100, 15 over square root of 40. Okay, but the one you have to show is the black one. Okay, this is what you need to show, because by definition, p-value is the probability of getting the test statistic. The test statistic, not the sample mean. The test statistic, or more extreme, given given that the parameter in the null hypothesis is true. Okay, that's why this is a test statistic. When the null hypothesis is true, then we compute the p-value. Okay, even though we know this will give you the same result. This will give you the same result. That's not how you show that. Okay, don't use this. Don't use this. Okay, even though we know that it will give us the same result, but no, that's not how we show that. Okay, that's for the p-value, and I wonder what you get. It's something very small. I get 6.81794 times 10 to the negative 8. Because we round to 5 decimal places, this is basically 0. Okay, if I want to write these numbers in decimal, that means this 6 here is at the 8th decimal place. That would be 0.1234567 8. That's the probability. Okay, that's the probability. Now, so assuming, basically, if we play the story back, assuming that the claim of that principle is not true, okay, he said that it is above 100 while it's actually just 100, the probability that we come up with the sample mean of 112.5, assuming the average is supposed to be 100, the probability that you can come up with that sample is near 0. Okay, but nobody, you cannot really say that there's something wrong with the sample, right? Okay, it could be wrong. There could be something wrong with the sample, but compared to the claim, okay, compared to the claim, at least my sample comes from a sample. I mean, that's what actually happened, right? It is possible that I actually manipulate my data. That's another story. But if the sample was done correctly, okay, I don't do any manipulation. I do random sampling, as being claimed here, right? Okay, if I do random sampling, and of 40 students, I get the average of 112.5, then either my claim is true, which means it's actually greater than 100, or my claim is false, that it is not above 100. Okay, but the evidence shows that yes, it is significant. The probability for me to come up with this average sample mean, with supposed average only 100, is near 0. Okay, so knowing that p-value, if my p-value is less than the alpha, that's where step 5 coming in. Step 5, informal conclusion. Then let's take a look. What do we do if we have the p-value less than alpha? We will say reject null hypothesis. Okay, if p-value less than alpha, we say reject null hypothesis. my p-value, which is 0, is less than alpha, which is 5%. It's less than that 5%. So we will do say reject null hypothesis. Actually, I have to change this. Let me write it in column. P-value is less than at 5%, therefore we say reject null hypothesis. Now, again, the one you need to write is the one in black. If I write it in red, you don't have to write. But I write it in red here so that you see the reasoning, okay? Then why do we reject null hypothesis? Well, because if 100 is the average supposed to be, okay, then it will be so hard to get the sample mean of 112.5. So it is more likely that the alternate hypothesis is the true one, right? That's why then we reject this. If alternate hypothesis is more likely to be true, then we will reject the null hypothesis. Okay? That's what we say there. If the p-value less than the significance level, the alpha, that's the one given to us, then we reject null hypothesis. Okay? Thomas, what happens if the p-value is greater than 5%? Then we will say fail to reject null hypothesis. Okay? In all times, they say accept null hypothesis. Do I say there? Yeah, in all time, they say accept null hypothesis instead of fail to reject null hypothesis. Okay, but that's still being used by senior statistician. Last year, I found one professor at UCLA still use this phrase accept null hypothesis. And my former students say, Thomas, what do I do with that? I said, no big deal. I did tell you in class that if your professor say accept null hypothesis, then accept null hypothesis it is. Make him happy. Okay, make him happy. Just make him happy. Okay, even though we know that more recent statistician will say fail to reject null hypothesis. Okay, I personally have no issue with somebody say accept null hypothesis. However, more and more statisticians recently prefer to say fail to reject null hypothesis. It has something to do with this notion. It's kind of strange, I know. It's kind of strange, but I hope by using this illustration, I can, you know what I mean. Okay, now it's about the following. How do we know? How do I know? Sorry for being too romantic. How do I know I love my wife? Now for you, how do you know you love somebody? Okay, is it because A, I can live with him or with her? Or I can't live without her? Which do you choose to define the word love? You see what I mean? Okay, so to define the word love, I will say my choice is the second one. I cannot live without her. Okay, I depend on her so much, right? Okay, and hopefully she depends on me too, right? Otherwise, that's one-side love, right? Okay, but yes, the reason I say that I love her and not somebody else is because I cannot live without her. Okay. Now, but for other people, they define the word love another way. Okay. They define the word love another way. They define it this way. Maybe instead of using the word love, let's use presidential election. I mean, not trying to be political, but I tried to explain to you what happened 4 years ago. It is a truth that most people don't like Trump a lot. But what happened 4 years ago, you compare that with Hillary. Okay? Now, simply because somebody choose Trump, does it mean that person like Trump? A lot of people who actually voted for Trump, I asked them, why do you choose or what do you vote in? And no offense, not trying to say that's wrong. Okay, everybody have their own choice, and they have all the right to choose whoever they want. They have all the right to vote for Trump or not voting at all. Okay, and the reason they give me, a lot of them, is not because they like Trump, but that's because they reject Hillary. Therefore, because they reject Hillary, therefore they accept Trump. Okay, do they support Trump? No, they don't support Trump. Okay, they don't like Trump themselves, but they accept it. I have no choice. I have to accept my wife, whoever she is right now. It doesn't mean I support the weakness that she has, but I just accept her because I love her. Okay. No, I'm not saying then these people love Trump. No. I suddenly changed my topic to my wife earlier. But when they say that they vote for Trump, that's because they say that they can accept Trump more than accepting Hillary, for example. Now, likewise, those people who voted for Hillary, for example, does it mean that they support, they actually like whatever she does? No, I don't believe that's the case. I don't believe there's nobody will love any politician 100%. Trust me. Okay? No. Okay. So when they say they actually voted for Hillary, it's more likely they actually prefer to say they can accept Hillary more than Trump. Okay? With all the weaknesses that Hillary had, for example, that person voted for Hillary because that person can accept Hillary more than Trump. Okay, so that's what happened 4 years ago. Now that's how then, I hope that explains why some people still insist that the accept null hypothesis is still acceptable. Okay, now I am actually one of them to say that I don't mind when somebody say accept null hypothesis. Okay, but in our test later on, I don't want you to say accept null hypothesis. Okay, I want you to use fail to reject null hypothesis. That's how you will say it. For us here, I don't think I will penalize you 1 full point or 2 full points, whatever number of points I assign for that step. But I will not give you a full point if you use this phrase instead of fail to reject null hypothesis when it's supposed to be fail to reject null hypothesis. Okay, I hope you accept the reason I want you to, when you have to say fail to reject null hypothesis and you end up saying accept null hypothesis, I will penalize you a little bit. Not because it is wrong, but it's because I need you to adjust to what most people use in statistic right now. Okay, that's the tradition, unfortunately. Okay, I'm sorry. Let me say that in advance. I'm sorry. I don't like to do that, but I have to do that. Okay, it's not totally wrong, but it's partially wrong for most people. Okay, so part of the job that statisticians need to do is to make people understand what you are doing. Okay, so it's not that you know what, Thomas, I want to do it this way, you have to accept it. No, the thing is, as a statistician, when you perform hypothesis tests, it's part of your job to make people understand what you do. Okay, yeah. So coming back here, I hope that explains why we say reject null hypothesis. Rejecting null hypothesis is strict. Once the p-value is less than 5%, then we reject null hypothesis. What happens if p-value is greater than? Then we
Thomas,
will say.
sorry, I was a little confused. So you wanted us to say accept or fail to reject?
fail to reject.
Okay.
Yeah. Okay. So maybe I put it this way with a box. If p value is greater than alpha, then fail to reject null hypothesis. That's what you should write. Okay. Historically, people use the phrase accept null hypothesis before they change to fail to reject null hypothesis phrase. Okay, let's do one more. Let's do one more. Can I ask you to do this question too? Do up to step 5. So the test statistic, I mean, the significance level now is 3%. Now, significance level is something you use in step 5 based on our procedure. If you use the traditional method, the critical value method, then test statistic will be used in step 4. Okay, but using p-value method, test statistic is being used in step 5. In other words, in your step 1, 2, 3, 4, you don't worry about test significance level. Did I say it right? Significance level only being used in step 5 based on our procedure right now, the p-value. We don't use significance level until step 5. But if we use critical value method in step 4, then significance level being used in step 4. Right now, we use that in step 5. Okay, what's the claim? I think the claim should be girls on average score higher than 600 on the SAT third course section. I think that's the claim. Okay, you do that too, please. You need to have hands-on experience in doing this. Step 2. We also happen to know that the standard deviation for all SAT verbal score is 100. Okay, standard deviation for, so the sigma is actually 100. The sigma is 100. The alpha is 3%. And then what's the n? A random sample of 20. Okay, so the n is 20. Okay, so hypothesis. Hypothesis mu is less than equals to 600. Alternate hypothesis mu is greater than 600. Okay, and alternate hypothesis is the claim, and because it's greater than a constant, that will be a right tail, just like before. Okay, my test statistic will be C equals to, what do I have on the top? A random sample of 20 girls give us a sample mean of 641. That's X bar, 641. So test statistic, 641 minus 600. The formula is X bar minus mu over sigma over square root of n. That is 641 minus mu, which is 600 from null hypothesis in step 2 over 100 over square root of 1. I get 1.83358. Now check my computation. I know mine is correct. I want to make sure you know how to use your calculator. The p-value, so I get standard normal distribution. Let's say this is the c-score equals to 0. Now I have c-score 1.83358, and I need to get the area away from the mean. Away from the mean. So the p-value is normal CDF (1.8335) to infinity 0. I get 0.033358. Am I right? Hmm. Okay, that's the p-value. So what can I say in step 5? In formal conclusion. Now notice that the p-value, the p-value is greater or less than alpha. My alpha is 3%. That's given in the question earlier. The alpha is 3%. Right? The alpha is 3% here, right? The alpha is 3%, and my p-value is 0.033 something. So which is greater? The p-value is greater, right? Now, because the p-value is greater than what we say. back. If p-value is greater than alpha, if p-value is greater than alpha, we say fail to reject null hypothesis. Fail to reject null hypothesis. And that's it. That's what you write. That's all you write. Okay. Now let's go on with the last step. With the last step. Step 6. I wonder why it keeps on changing here. And we can see some wording for concluding on our textbook, page 397. The wording is actually, you can see it on figure 8.7. Now, if you have your textbook, please open your textbook. Okay, they give you the wording we need to use on our final conclusion. And some of them are the following. There is sufficient evidence to warrant rejection of the claim that blah, 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 blah. There is not sufficient evidence to warrant the rejection of the claim that blah, 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 blah. Okay. The sample data support the claim that blah, 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 blah. There is not sufficient evidence to support the claim, blah, 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 blah. Okay, now the thing is, our textbook, if you follow our textbook closely, you will see the way they do the final conclusion always follow those, either one of those 4 according to the cases they provide. But it's actually not that strict, not as strict as what they provided. You can say the following. You can say the sample data support, the sample data does not support. Okay. The sample data support, the sample data do not support, or there's sufficient evidence to support, there's sufficient evidence to reject, and blah, 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 blah. But in every sentences, every conclusion you draw, you have to rephrase, you have to copy paste the claim again. Okay, so even in our textbook, in all 4 cases, they always give the original claim. Okay, now, so those are things you need to do. The one that you are not that strict is you don't have to follow the wording from that figure 8.7. Okay, you don't have to follow that. But in every conclusion you give, you always need to copy paste the claim again. So for example, to be more, suppose I write this, the sample data do not, or does not, I don't know what is the correct one, do not support the claim. Now you cannot stop here. You need to copy paste the claim. What is the claim? That, for example, that the principal, blah, 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 but whatever you say in your step 1. Whatever you say in your step 1. Okay, you have to say it again. You have to say it again. Whatever you say there, that's what you say here. Not a single word off. Okay? Not a single word off. Whatever you claim in your step 1, that's what you write again here. That's why when you do the claim in step 1, we try to have a short sentence so that you don't need to write a long one later. Okay? At the same time, of course, we don't want to claim something different from what the question wants you to do hypothesis testing on. Okay, now next, next, let me erase that first. The no-nos, the sudden death. Like if you do these 2 things, then I have to mark you off right away for that last step. First one, Avoid using the word I or we. Do not say I support the claim or we support the claim. No, we are not putting ourselves on the fire line. We are not the one who do the judgment. We are just administrator. Okay, the real judge is actually the sample data, the evidence. Okay, it's the evidence who support or not supporting the claim. Okay, not I, not we. Okay, second, avoid you to use the word proof. We are not proving anything because what? The sample data or the evidence that we use itself may have sampling error built in them. Okay, and because of that sampling bias, okay, it is possible that the claim is true, yet we reject them. It's like this. It is possible that I'm so good in statistics, but when I took a test, I failed it. It's possible. Okay, why? Because who knows? I have an accident, I have a headache, or I need to help my wife the day before that I didn't have time to study, right? Okay, that's why it's never correct to judge somebody passing or not passing this class by only one test. I cannot give only one test. Okay, however lazy I am as a teacher, I cannot give you only one test. It's like all your grade depends on your final. No. Okay, can a teacher do that? Yes. Okay, that's well within the right of a professor. Okay, but will I do that? No, because I don't want to misjudge you. Okay, okay. The procedure itself by judge like trying to pass somebody or fail somebody based on only a sample size of one is a big bias there. Okay, that's why instead of only giving you a final, I give you a mid test too. Right? Even the midterm test, instead of giving you only one, I give you 4. That way I have enough data, okay, to perform this quote unquote hypothesis testing. So when I later on decide, okay, you know what, I pass this person or I don't pass this person, I base that on the data and not a sample size of 1. Not even sample size of 2, I have sample size of 5. Test 1, 2, 3, 4, and final, and hopefully your quizzes help you. Now, of course, if your test 1, 2, 3, 4, and final almost 68, but then your quizzes that's supposed to help you to pass is something you don't even turn in, then of course nothing much I can say, right? You basically don't provide me enough evidence to pass you. Okay, it's your job to provide me enough evidence, a good sample data that I have reason to pass you. Okay, that's the idea. Okay, but what I do here as a professor is basically to administer using statistics. Okay, now if I later on let you pass, it doesn't mean I prove that you're supposed to pass. It simply means the data, the evidence I get from you show that way. Okay. Now, actually, on the other hand, suppose I later on don't let you pass, it doesn't mean you don't know stats. No, that's not what it means. It simply means the sample data that I have is not sufficient yet to pass you. Okay. You simply don't provide me enough evidence yet. Okay. So you can repeat it in future and provide the next professor with a better data. Okay, then and of course that data must come from some knowledge, right? Okay, but when I do hypothesis testing, when we do hypothesis testing, we never use I or we in our conclusion. We always use the sample data. It's the sample data who provide the judgment. I'm just administering it, okay? And because the sample data may have some sampling error or sampling bias built in that, okay, there are something called non-sampling error, non-sampling bias also, okay? But that one we may be able to avoid, but sampling error, the error that comes from the sample is something we cannot avoid. It may happen, and it is possible that the sampling bias is so big such that we say the claim is not true. So it can go either way. So avoid using the word proof. Okay, that's a big no-no. It's a big no-no. It's a big no-no. Okay, we have seen many story that shows somebody is actually so smart, but it doesn't show in that person's life until much later. Okay, we also know, for example, one of the great person in science, Newton, there's some rumors saying that he was not doing well at school, right? Albert Einstein, I heard, or I heard some rumors, I'm not sure if that's true, that he was not doing well at school also. Okay, but those are just the evidence not showing yet. Okay, the evidence not enough yet, and the teachers actually took in their own hands saying that I don't think you will be successful. You know, no. As a professor, as teachers, we only administer and do the judgment based on the evidence. Okay, yeah. So, well, in case one day later on you kind of like not making it yet in some part of your life, don't give up. Okay, don't get discouraged. Tell yourself, you know what, I just don't provide enough evidence for now, but I can do it. I can do more. I can do better. Okay. Now, let's apply this in the questions we have above. Suppose I go back to this question 2, the most recent case. Suppose we want to test this situation here, and then we come up with informal conclusion, fail to reject null hypothesis. Now, if we fail to reject null hypothesis, so which of these two that we support? Do we support the null hypothesis or the alternate hypothesis? If I say fail to reject null hypothesis, that's right. We support null hypothesis and cannot accept that yet. Okay, that's informally though. Okay, formally what we say is fail to reject null hypothesis. Now, if we say we support null hypothesis, take a look on your hypothesis again in your step 2 here. Okay, where's the claim? The claim is with the alternate hypothesis, but that's not what we support, right? That's not what we support. So we will say in our conclusion the following. Conclusion. Now I have a habit in my conclusion. I always insert the significance level. I say at 3% significance level. More and more actually doing that, but you don't have to. Then I say the sample data do not support the claim that girls on average score higher than, what did I get? Score higher than 600 on the SAT verbal section. On the SAT verbal section. Now, that's a very quote unquote cheap way to conclude, but that's not wrong. Doesn't matter. Cheap is okay. Now, you may want to word it another way, for example, or you may say at 3% significance level. Again, if I write it in other color, you don't have to do that. You may say this is the following wording is actually a more precise wording. There is insufficient evidence to support the claim that girls on average score higher than 600 on the SAT verbal score, verbal section. Okay, you can do this kind of wording too. So there are many ways to word it. Just keep in mind, do not use the word I or we. Do not use the word proof. You always need to compare the sample data, which is your evidence, against the claim. Okay, so you can say the sample data support or do not support. There's sufficient evidence or insufficient evidence. In fact, our textbook on that page 397 says that there are times we may need to use multiple negative. Like for example, somebody may use the phrase there's insufficient evidence to reject the claim. Okay, in other case, I think that could be the case we have in earlier question. No, I don't think so. I don't think so. Can you try to draw conclusion from question 1? Can you try? I hope you take some notes. Otherwise, then you need to look at the whole picture here. Let me pull it up a little bit. Yeah, you can see better. So this is question 1. The claim is the average IQ of students in principal school is above 100. And then in step 5, we reject null hypothesis. We reject null hypothesis, so this is what we support, right? This is what we support. And the one we support happens to be the claim. Okay, so we then support the claim. Okay, so we then support the claim. Step 6, conclusion. What's the alpha? 5%. Okay, so at 5% significance level, at 5% significance level, there is sufficient evidence to support the claim that. Now you cannot start by just saying to support the claim period. No, you have to go on. What is that claim? That claim is the average IQ of students in principal school is about 100. Now, I purposely show you what I do here. Of course, I don't think that's what you can do in your test, though. You cannot do copy and paste, right? Okay, but that's what you're supposed to do. Okay, that's what you're supposed to do. You basically need to copy whatever you write in your claim again. Now, I'm about to give you some examples to do on your hands-on experience. Okay, you will see that your test 4 is mainly on hypothesis testing. So I need you to be very strong in the structure and of course drawing conclusion too. That's including. Okay. Now, what did I want to say earlier?
Just a quick question, Thomas, before.
Huh?
Yeah. Do you think we will ever encounter a question so to let us test at different significance level in the same question?
No, no. In other words, when we do hypothesis testing, at least in our class, I have to provide you the significance level.
Okay.
Yeah, I mean, the hypothesis test will be done at only one significance level. Even though, I mean, even if I give you like, okay, you know what, test it at 3% and then test it at 5% in part B, for example, okay, then what you need to repeat is actually step 5 and step 6 only. You see what I mean?
Yeah, thank you.
Mm-hmm. Okay. What did I want to say earlier? The wording. Oh, you know what? How people lie, how statisticians lie in hypothesis when they perform hypothesis testing. Here, one way we know that somebody's lying. Now, you have life experience too. I don't believe if you can tell me that you never lie, right? Now, how do we know people lie? How do we know people lie? How do we detect that? Okay, there are some ways to lie. The first one is not telling the truth. When you have to tell the truth, you are not telling the truth. Okay. Now, definition of lie is not only telling not the truth. No. Okay. Especially in the court of law, you are lying if you are not telling the truth, not if you tell not the truth. Okay. That's including if you are silent. Okay. That's one. Okay. Second, but not telling the truth is clear, one way of lying. But how do people lie also? How do people lie? Another way people lie, especially in journalistic, when you read news, okay? It's mixing truth and opinion. That's actually one way to lie. So I kind of like mixing my opinion together with other truth and present it as one package. So when you read news, okay, even though they kind of like present to you what happened, what we call facts, right? But in between, you need to also pay attention on how they interpret the incidents, the facts, and you have to take that as an opinion. Okay. The third way is presenting a conclusion not in the claim. So basically the claim say one thing, the conclusion say another thing. Okay? The claim say one thing, the conclusion say another thing. Now I give you one recent example. I don't know if you follow the presidential briefing on this COVID-19. I do. It doesn't mean I believe by our president that much, okay? But he has to present something, and there must be some facts that I can accept in his presentation. There are some opinions too. I somehow think our current president is bragging about himself a lot. Okay, so, but I mean, if you can put that aside, there are things that he said that actually acceptable as a fact. Okay, yeah, not all though. That's what I mean. Okay, that's why that's where this case actually coming in. I hope you realize, right? Okay. he is someone who likes to mix the fact with his opinion. And therefore, when we listen to him, you need to be careful. Oh, you know what? I accept this one. You know what? This one, yeah, you know what? Let him talk. I would just like, yeah, whatever you want, Trump, right? Okay. Now, one of the case that happened recently is that he said that oh, you know what? We already have the best test that we have so far for COVID-19. And then one of the journalists say that, is it about competition? So he said something about we have the best test in a sense that that's the best we can do right now. We have 3 different tests, the PCR test, rapid test, and then swab test, whatever that is. Okay, so basically we have enough tests, we have the best, we can test from different point of view. Do you have the antibody? Do you have the virus? Is the virus still active or the virus already shed out? Okay, but then somebody else, a journalist, actually interpret the word best there and say, is it about competition? You know, and then the president, as usual, with his alpha male mentality, I guess, he just said, you know what, I go to another journalist, or just kind of like wave that person's question off. Now, of course, I think it starts from a misinterpretation of what he say, and he get pissed off. Okay, but this is what actually happened with when you present a conclusion that is not in the claim. Okay, so if you ask me to defend that conclusion that I didn't make in my claim, I cannot defend that conclusion because that's not the claim I make anyway. You see? Okay, so that's why when it comes to hypothesis testing, whatever you say in your claim, you have to say that exactly the same way again in your step 6. Okay, not enough to say to support or not to support the claim, period. No, you cannot stop there. You have to continue that whatever you say in your step 1. Okay. So that's where people maybe kind of like make up stories. You know, that's another way that they present a conclusion, not in the claim. So going back to the story I told you earlier about the presidential briefing. Now, I'm not defending president in this case, okay? I'm just showing you as a case where he says something and the journalist actually conclude another thing, kind of like pick and choose his sentence and make it against him. In that situation, of course, the president has no way to support that conclusion because that's not the claim he made. Okay, when he say the best there, not in sense of competition, but in sense of, you know what, this is what we can do so far. That's the best we get, and that's what I try to present to the country. Okay, you know, in my opinion, this is my opinion. I'm not saying this as a fact. This is my opinion. Okay, I'm not against him or not to support him, but he's a person. Okay, trust me. Well, like what I said in class, if you put Thomas to be the president of the United States, I already sell this country. It would be worse if I were the president. Okay, so I don't expect a perfect president too. But at the same time, yeah, there are things that he can say nicer. Okay, it's so hard to be a president, huh? Yeah. In fact, it's so hard to even be a professor, stats professor. Trust me, I get a lot of complaints. So that's about the conclusion. I don't know why every time I move this, you noticed that I changed this earlier, right? I already changed this earlier and it went back to 1, 2, 3. No, that's not what I want to do. I want to change this. I want to change this becomes, it should be my A. Okay, I would like you to do some hands-on experience. Let me get it from my old notes here. Hypothesis testing procedure. Okay, let's do this one. Let me change the wording a little bit. Does it take it as wonderful? Take it as a picture, huh? Anyway, assume the standard deviation here to be, assume the standard deviation here. This is actually a sample standard deviation. It's supposed to be, it's supposed to be S equals to 25.6. For now, use as sigma equals to 25.6. Okay, try to do that. This is the actual question I get from Boston University School of Public Health. As I remember, this is the question they use in their survey for their Masters of Public Health. Okay, let me give you maybe around 6-7 minutes for this, or maybe 8 minutes from now. So right now it's 10:32. We come back at 10:40. With you are done with all 6 steps. Okay, let's start. Step 1. Oops. Step 1. The claim. The claim is the weights the mean weight for men. I have to rephrase it in this case. The mean weight for men is higher than 191 pounds. So here we need to rephrase it, right? Now, of course, you don't have to rephrase it exactly like mine here, but I don't think you can rephrase it other way though. Anybody can give me an option besides how I rephrase it? Okay, nobody say anything. Okay, I go on. Hypothesis. The null hypothesis is mu less than equals to 191. The alternate hypothesis is mu greater than 191. Step 3, test statistic. Now here I need to warn you ahead that from the wording, a random sample of 100 American males in 2006 turns out to have an average of 197.1 pounds with a standard deviation of 25.6. From the wording, then this 25.6 actually refers to a sample standard deviation. Okay, it comes from sample, not the hypothesis, not from the population. A random sample have this average with this standard deviation. Okay, so what I do here to adjust that with what we have learned so far, we assume sigma to be 2.56 for now. Okay, so then the test statistic will be Z. And the sample mean 197.1 minus 191 over standard deviation 25. Actually, it's 2.56 or 25.6? 25.6, my bad. That's 25.6. 25.6. So that's 25.6 over square root of 100. So I wonder what I get. 6.1 times 10, 61. 61 divided by 61 divided by 0.5.6 is 2.38. 2.3828. Okay, so in my p-value, I have standard normal distribution. Oops. I have standard normal distribution. This is the C equals to 0. This is the C equals to 2.38281. And I need to find the tail area away from the mean. So my p-value will be normal CDF two point three eight two eight one E 9901. I get very small, 0.00859, which is smaller than the alpha 3%. So my informal conclusion will be reject null hypothesis. Again, because my p-value is less than alpha. My alpha is 0.03. Therefore, the conclusion will be we reject null hypothesis, but where's the claim? The claim is here, higher than 191. We did right test earlier, right test. So the conclusion will be at 3% significance level, there is sufficient evidence to support the claim. Thomas, do we support the claim or we reject the claim? In step 5, you say you reject null hypothesis, Thomas. Yes, I reject null hypothesis. I reject null hypothesis. This is what I reject. But if I reject the null hypothesis, it means I support the claim, right? Because the claim happens to be the alternate hypothesis, not the null hypothesis. Okay, so yes, I reject null hypothesis, but the claim is the opposite of null hypothesis, therefore I support it. So to support the claim that, what did I say in my claim? The mean weight for man, the mean weight for man do I say man or male? Yeah, for man. For man is higher than 191 pounds. Okay, so that's what it's supposed to look like in our full hypothesis testing here. Step 1, step 2, step 3, step 4, step 5, step 6. And I need you to give me these steps. I need you to write me this. I need you to write this. 1, 2, 3, 4, 5, 6. And you have to do it in that order though. What I don't want to see, honestly, I saw this before. I get a big piece of like 1 here, and then 2 here, and then 3 here, and then 4 here. No, if you do it that way, then don't make it 1, 2, 3, 4, because your 1, 2, 3, 4 seems to be more like 1, 4, 3, 2. No. Okay? No. 1, 2, 3, 4 implies the order. You do this first, and then that one, and then that one, and then that one, and then that one. Thomas, you are so picky. I'm picky. Once you step out there in the real world, you think people not picky? I'm just trying to train you to live in the real world. Okay, let's go on. Thomas, but that's if we assume the sigma, the standard deviation there is from the population, right? But the actual question actually give the sample standard deviation, not population standard deviation. So suppose I do this as supposed to be. We go back, we treat this standard deviation as supposedly. S equals to 25.6. Then what happened to the test statistic? Just like what we had in confidence interval case, if we have sample standard deviation instead of population standard deviation, then we will use t-test. Okay, and the formula is very similar, is x bar minus mu over, we replace the sigma becomes S. Okay, that's the only difference. We replace the sigma population standard deviation by sample standard deviation, and therefore the C score, the standard normal score, now change becomes T score. That's basically the only difference. Okay, now then when I compute that, believe it or not, you'll get the same value. Don't you think so? But it's not C score anymore, that's a T score. 2.38281. Okay, that's what will happen in our test, step 3. Now, how about our step 4? So let me kind of like break it here. In our step 4, the p-value, we still perform right-tail test. Okay, we still perform right-tail test. And t-distribution looks very, very similar to standard normal distribution. At this time, instead of c, this is t equals 0, and this is t equals 2.38281. Now, the p-value, therefore, the p-value is still the area of this tail. Okay? Now, but when we compute that, we don't use normal CDF. We will use TCDF. Now, can you do that? TCDF, the notation will be for TCDF, that will be left fence, upper fence, lower fence, upper fence, and then degree of freedom. That's the notation. So for us right now, this will be 2.38281 E99, and the degree of freedom is 99. The sample size is 100, right? Okay. So then you use your calculators, TCDF. Let me show you my calculator. You will do TCDF. Right? You go to TCDF. Oops, sorry, not this one. Okay. Not this one, this is wrong. This is wrong, clear. So TCDF number 6. I happen to press number 7. Enter. Now the lower in this case is 2.38281. That's the lower fence. The upper fence is E99, right? E99. And then the degree of freedom is 99. It's one less than the sample size. Enter. 0.00954. 0.00954. 0.00954. And you notice that we still come up with the same conclusion, informal conclusion, that the p-value is less than alpha, right? Happens to be in this case. That's usually the case, by the way. That's usually the case. That's usually the case. Therefore, my step 5 will be the same. Informal conclusion. Informal conclusion will be reject null hypothesis. And finally, the step number 6 will be the same. Okay, even our step 5 already the same to what we have earlier. Okay, so I hope you see the difference between if we are testing with sigma known then we will use C equals to X bar minus mu over sigma over square root of N. Now, suppose sigma is unknown. Then, if sigma is unknown, then we use S, sample standard deviation, in place of sigma. Right? Then if that's the case, we use T equals to X bar minus mu over S squared over square root of N. Okay, let's look back. Last week, I did mention that. Last week, we have that here. Okay, we have it there. If we are testing population mean with sigma known, this is the formula. What happens if sigma is unknown? Then we will change the C becomes T in that formula and sigma becomes S. That's the difference. Okay, that's the difference. So going back to this hypothesis testing example we did earlier, the change will happen with the step 4 and step 5 only. I'm sorry, I should say step 3 and step 4 only. Okay, the only change will be in step 3 and step 4. Now, I would like you to do example 2 together with your break. Let's see, where's my example 2. The thing is, you need to be able to interpret the question though. Interpret the question. From that question, you need to be able to see if the standard deviation is from population or from sample. Okay, so this is your example 2. Problem 2. I think this one is nice. They say the test if whether assuming the population standard deviation is 8 ohms. This question is the actual question I picked from University of Utah from their electrical and computer engineering department. So basically they try to test the resistor from a manufacturer, and they found that the average is 102 ohms. Okay, while what they need is 100 ohms. Let me ask you to do this together with your break, 10 minutes break. And I assume it will take you around 10 minutes to do this. We come back at 11:20. Okay, let's start. This is what I get in the first 3 steps. Now then, if you see again, it's a two-tailed test. So I need to find the area here and the area here, which is the same to the area there. Okay, so what I will do instead is I will find the area of one tail and then multiply it by 2. So the p-value will be 2 times normal CDF 2.5 to E99 0 1. Don't forget to multiply by 2 after that though. Okay, so 2.5 E99, I get 2 times 0 0.00621. I get 0 0.01242. Again, because this is a two-tailed test. Okay, that's why I need to multiply by 2. Then step 5, informal conclusion. Informal conclusion, the p-value is less than 5%. The the significance level, so we will say reject null hypothesis. Okay, then step 6, conclusion. The conclusion is at 5% significance level, there is actually there is the sample data. Why we do 2 times normal CDF? Because two tail. Because of two tail. So when I compute this normal CDF here, that's only the area of one tail, right? Now I multiply that by 2 because of two tail. Okay. There is insufficient evidence to support the claim that the population mean is 100 ohms. That's for this example 2. Now, what if, just out of curiosity, what if I change this instead? I change this instead becomes S. So instead of using sample population standard deviation, we use this as sample standard deviation. The change will be in step 3. Step 3, instead of Z test statistic, I use if, okay, if. Then the test statistic instead will be T equals to 2.5. And then step 4, the P value will be, the P value is 2 times TCDF 2.5 E99, degree of freedom is 0. I get 0.01406. So I still come up with the same informal conclusion and therefore the same conclusion. Okay. Now, I hope you see the difference between, if the sigma population standard deviation is known and if we replace that by S sample standard deviation. Now let's go on. Other questions. The following is from New York University School of Business. Give me a second, let me quote that. Problem 3, New York University, Denver School of Business. I somehow think Denver is in Colorado. I'm not sure. Okay, a healthcare actuary has been investigating the cost of maintaining cancer patients within its plan. These people have typically been running up cost at the rate of 1,240 per month. Now, a sample of 15 cases for December. The first 15 for which complete records were available, and an average cost of 1,080 and standard deviation 180. Is there any significant change? So let's see what we know. What we know is the sample size is 15. The sample mean is 1,080 and sample standard deviation, right? It's not population. How do I know? Because when they say this standard deviation is in the context of these 15 cases. You see? Okay, is in the context of these 15 cases. So that's the sample standard deviation instead of population standard deviation. Now, people typically running up costs at the rate of 1,240. Is there any evidence of a significant change? Now, they don't tell us the alpha in this case. What happens, Thomas, if they don't tell us the alpha? And the default we use, if alpha is not given, is 5%. This is the default significance level. Okay, so if I have a question that I don't tell you the significance level, or has very likely because I forgot, then we use alpha equals to 5%. Okay, that's actually the tradition though. That's actually the tradition. Okay, now then, what is the claim here? Let me start from here. The claim. Is there any evidence of a significant change? What change? The cost of maintaining cancer patients has changed from 1,240. Cost. This is where I need to rephrase it. Of maintaining cancer patients is 1,240 per month. $1,240 per month. And we want to see if that had already changed hypothesis. So the null hypothesis is mu equals to 1,240. And the alternate hypothesis mu is the complement effect. So you see, I hope you see that even better now, that the claim does not need to go to the alternate hypothesis all the time. No, it is possible that the hypothesis goes to the null hypothesis, that the claim goes to the null hypothesis. And in this case, we get a two-tailed case again. Then our step 3, I actually can ask you to do this, right? Don't you think so? Can you try to do this? Statistic. Use t equals to 1,080 minus 1,040 over 180 over square root of 15. I get negative 3.4425. Step 4, the value this is my t equals 0, this is negative 3.4465, but it's two-tailed. So I need to find the area here and the area here together. So p value will be 2 times TCDF negative infinity to negative 3.44265, degree of freedom 14. That's 0.002 times of that. 2 times that. 0.198, which will be 0.00396. It's very small, huh? That's very, very small. So my step 5, informal conclusion. Do you hear some noise, by the way, a baby noise?
Just a little bit.
Just a little bit. Yeah, it's my turn actually to take care of my baby. See that? My baby. And behind her is actually my in-law stuff. I have my father and mother-in-law staying with me for the last 5 months. Actually, 4 months something. Okay, let's come back here. Okay, we reject null hypothesis. So step 6, the conclusion. Why two-tail? Well, because of this. Because of the claim earlier. Because of the claim is equal to, right? It's equal to, okay? So the complement is not equal to, so to show that it is not equal to, then I need to show that the p-value is very different from 0, okay? It very different, can be much positive or much negative, okay? Yeah, so every time we have two-tail, every time we have not equal sign here, then we will do a two-tail test. Okay. Now let's go back. So what will the conclusion be? The conclusion will be at 5% significance level. Because I didn't say what's the significance level, then by default it will be 5%. The sample data do not support the claim that the cost of maintaining cancer patients
So in the future, if we don't see a significance level, do we just assume 5% for all the problems?
Yes, that's right. 1,200 Okay, so the claim is not supported, by the way, permanent. In fact, what we see here is actually less than that, right? Yeah, it's actually. Now that's for this question. Let's do more. Let's do more. Let me see my question number 4. Oh, this is something new. This is something new. So I basically transitioned to something new. Question from University of Notre Dame, Department of Sociology. The mayor claims that blacks account for 25% of all city employees. A civil rights group disputes this claim and argues that the city discriminates against blacks. So I assume, yeah, this is the city employee. Not employees in the city, but the employees working in the city hall maybe, okay, by the government. So a civil rights group disputes this claim and argues that the city discriminates against black. A random sample of 120 city employees has 18 blacks. Test the mayor's claim at 5% significance level. So this is not testing the population mean anymore. This is testing a proportion. Okay, this is testing proportion. This wording here, that will be the claim, but that's actually on the proportion. So let's see, the sample size is 120. The number of blacks among that sample size is 18. So from here, later on, you will see that the p hat is 18 over 120. I think that's 15%. And then the significance level is 0.05. Then if the sample proportion is 15%, is it something close enough to what the mayor claimed, which is 25%? Okay, so, but Thomas, don't you think it's possible it's because you don't sample enough employees? Well, how many employees a city have, by the way? Right? Let's say it has like 200, then 120 is actually quite big already, right? Okay, but you can sample more if you want, right? But how big is then we have to say that, you know what, we need to stop somewhere and just say that the mayor's claim is supported or not supported. Okay, so let's see, what's the claim? Let's use the mayor's claim because that's what we are testing here. The claim is blacks account for 25% of all city employees. That's the claim. Second hypothesis. And we have null hypothesis, alternate hypothesis. But the hypothesis now is on proportion, right? Proportion P, not mu anymore. And the mayor claimed that the proportion should be 25%. So to show if the mayor claims is being supported or not, we need to come up with a sample that is significantly different from 25%. If you want to say that the mayor claims is not supported, okay, then you need to come up with a sample proportion, an evidence that is significantly different from 25%. If you come up with a population, a sample proportion which is 24.8%. Yeah, it's different from 25%, but come on, how different it is, right? If it is only 24.9% or 24.8%. Of course, it depends on the sample size though, okay? But how we need to come up with something quite different, yeah, to say it's different, okay? Just a little bit different, come on, you know? Just like when Thomas said that a lot of people don't like President Trump, I'm not taking a sample of one or two people and claim that a lot. No, I mean it is the fact that we know a lot of people don't like him. That's why then we say a lot of people don't like him. Okay, but too bad though. We like him or not, he's still our president. So hang in there for a couple more months maybe. Okay. And Democrat better come with a better candidate, you know. Okay, otherwise, then we may have to accept this Trump again. Yeah. So don't blame only Trump though. If he get elected again, however much you don't like him, if you cannot offer someone better than him, do you think Joe Biden is better than President Trump? That's the question. We will see the answer in November, right? Okay. Yeah. Let's see, that's the hypothesis. Then how about the test statistic? One way to guarantee that Trump win again is by offering Thomas and as the opposing candidate. Then Trump will win again, trust me. You don't want Thomas to be there. The test statistic, now we cannot use, we are not using T. Okay, T is when you test the mu with sigma unknown. Okay, and we are not testing mu with sigma known. We are testing proportion, testing P. Now, if you look at our confidence interval, which I hope you did your homework, okay, you notice that when we do a confidence interval for proportion, the test statistic is standard normal distribution. The same to the test statistic when we on the critical value. I'm sorry, the critical value we use when we construct confidence interval for mu with sigma known. Okay, so in this case here we will still use Z, but the formula is slightly different. There will be P hat minus P over square root of PQ over N. That's the formula, which I mentioned in our handout in 8.2. Here. Okay, I hope you can see that clearly. Okay, so going back there, so the test statistic will be a C-score. Test statistic will be C-score. It's P hat minus P over square root of PQ over N. No hat here, no hat here, no hat here. We don't use hat in under that square root. No. Maybe I write something to remind you that in confidence interval for T, the margin of error, step 2, margin of error is critical value times square root of P hat Q hat over N. Okay, however, when it comes to hypothesis testing, there is no hat here. We will not use hat in our hypothesis testing. We don't use hat. Okay, now let's plug in numbers. This will then be equals to 0.15. That's the sample proportion minus the population proportion they claim, the mayor claim, over the square root of the P is 0.25, therefore the Q is 0.75 over the sample size 120. I get negative 2.52982. Please make sure you have the same situation with your calculator when you use your calculator. So on the top, I get 0.15 minus 0.25, close parentheses, divided by the square root of 0.25 times 0.75 over 1. That's what I get. Going back there. Now then, can you do the p-value? Is it left tail, right tail, two tail? Because this is not equal to, then it will be a two-tail test again. Okay. And suppose this is the standard normal distribution, and this is z equals to 0. My negative 2.5 is here, but I need to make it two-tailed. I need to find the area here and here. So the p-value will be 2 times normal CDF negative E99 negative 2.58201. I get 2 times 0.00571, which if I multiply by 2, I get 0.01141. It's supposed to be 2 if I use that. Well, that's it. What's the alpha? 5%. So informal conclusion. You tell me, do I reject null hypothesis or fail to reject null hypothesis? Okay, nobody say anything. Well, the p-value is less than 5%, which is the alpha, so we will reject null hypothesis. In step 6, the conclusion. At 5% significance level, the sample data will not support the claim that black let's account for 25% of all CDA. Okay, I hope you find it to be okay. It's very similar pattern to what we have learned before. Okay, this is the first time we deal with population proportion case testing, population proportion, first time. But the structure, I hope you still see this to be the same. Okay, the change actually happens here and here. Okay, but step 4 and on are the same. Yeah, the step 4 and on are the same. Now, with that said, let me ask you to do more problems. This time, I would like you to do question from here. University of Washington, Department of Statistics. Okay, let me give you maybe 10 minutes for this. Maybe 5 minutes. Don't rush though. I know in 5 minutes you may not finish yet, but then I will start working on this in 5 minutes. Let's see what we know from this question. Chris works for Mesa Air Pollution Study at University of Washington and studies the correlation between air pollution and the disease of atherosclerosis. Atherosclerosis is something to do with your artery, I believe. I think it's that one. You can find it. You can Google it. Okay. Now, nationally, so this is what we know in general, that 40% adults suffer from this disease. Now, Chris suspects that the proportion of people with atherosclerosis is in higher pollution area is higher, so greater than 40%. Okay, so then in the random sample of 600 residents, so that's the N, he finds 290 have atherosclerosis. At 1% level, that's the alpha. Is this good evidence that people in high pollution areas are more likely to have atherosclerosis? So let me help you write down what we know. The N is 600. The X is 270. So the P hat is 270 over 600 divided by 3. That's 0. Oops. It's 0.45. That's the p hat. While the alpha is 0.01. Okay. And the claim is either you have to parallel claim here. Either you use this one, proportion of people with atherosclerosis in high pollution areas is higher, or people in high pollution areas are more likely to have atherosclerosis. Okay, you can use either one of them. Happens to be both the same. Okay, you can use either one of them. I give you 5 minutes from now. Very likely still working on this. You can continue, okay, while I also start working on this. The claim. More likely means higher proportion. So higher than the national number 40%. So this is less than equals to 40%. And step 3, let me do my step 3 here. C is equal to P hat minus P over square root of P times Q over 600. By the way, because my P is 0.4, then my Q is 1 minus that 0.4. This will be C. Go to my calculator. Point 0.45 minus 0.4 those purposes divided by the square root of 0.4 times 0.6 over 600. 2.5. Exactly the same number I had earlier, huh? What a coincidence. Okay, 2.5 is 2.5 and step 4 key value this is when C equals to 0. This is C equals to 2.5. And I need the right tail, right? The right tail. Oops. Okay. Then what do I get for my P value? P value is 0. P value only one tail, so I don't need to multiply by 2. Normal CDF 2.5 EU99 0 1. Get 0.00621 such that when I go to my step 5, let me squeeze that in here. Step 5, informal conclusion. I will reject null hypothesis because my p value is less than alpha. Right? My p value is 0.01 and this is less than 0.01. So step 6, conclusion. Notice that I reject null hypothesis. I reject null hypothesis. But where's the claim? The claim is here, right? The claim is here. From step 5, we reject null hypothesis. So I support the claim, right? I support the claim. I reject null hypothesis, but null hypothesis and claim not always on the same side. So at 1% significance level, there is sufficient evidence to support the claim that people in high pollution areas are more likely to have atherosclerosis. Okay, that's for one hypothesis test. Would you like to do more questions on this? Let's do one more. Let's do one more. You do it this time, okay? You do it again. Problem 6. University of Irvine, School of Information and Computer Science. Okay, this time I give you 10 minutes. Now 5 minutes, 5:06 to start. I did the first 2 steps. Now the wording for your claim may be different from mine, and that's fine, okay? And that's fine. The keyword is it will be more than 15%. Now you may phrase the claim as the FDA reject the drug. Okay, you may also phrase the claim as the FDA reject the drug, but then in your hypothesis, you will have you will be the same with mine. Now, in my opinion, when you do hypothesis testing here, it's much higher preferable to have in your claim, you state something to do something with the parameter and the constant. So I don't mind you to say the FDA will reject the drug, but other instructor may not like that. Because from what we learned in this section here, in this chapter, the claim supposed to contain the parameter or implicitly contain the parameter, the constant of the parameter, okay? So this is preferable, even though I have to admit, if you would have said the FDA will reject the drug, I don't mind. Okay, let's go back. Step 3, statistic.
Wait, Thomas, in step 2, where did the 0.18 comes from?
Oh, from nowhere. My bad. Should be 0.15. Yeah, thank you.
Sure.
Test statistic Z equals to 0.20 minus 0.15 over square root of 0.15 times 0.85 over square root of 400. I mean, over 400. So what did I get here? I get 4.80056. And then step 4, p value, that's a right tail. Let me draw it first, just to make sure that I get it right. C equals to 0 here, C equals to 2.80056, and I need the tail area to the right, the right tail area. So p value, then drop it down a little bit. Oh yeah, it's okay. P value is CDN 2.80056, E9901. I get 0.00255. Now in step 5, informal conclusion. That will be reject null hypothesis. And then step 6, conclusion. At 5% significance level, there is sufficient evidence that to support the claim that more than 15% of population would suffer from mild nausea as side effect. Okay, that's for example number 6. Now, if we look back what we have done so far, let me use another color so that we don't get confused. What we have done so far are the following. On the confidence interval, I have done a confidence interval for mu with sigma known, for mu with sigma unknown, for p, and for hypothesis testing, I have done the parallel. sigma known and for P. The one that I have not done, and I'm about to do that in the next 40 minutes, is confidence interval for sigma squared or sigma. And from there, we will do the hypothesis testing for those. Okay. Now, I will come back to this hypothesis testing example, but I will do this confidence interval first. Remember, I told you last week that I need you to program that chi-squared distribution. I wonder if you remember that. Inverse chi-square. Inverse chi-square distribution. Yeah, we need that for this confidence interval. Okay, yeah, we need that for the confidence interval. Now let's go back. Let's go to a new sections. Basically, we look back to. Sorry, right there. That's from 7.6. Oh no, sorry, 7.5, not 7.6. 7.5. From 7.5, confidence interval for sigma squared or sigma. Now, when we do confidence interval for population variance or population standard deviation, one thing need to be said first that sample standard deviation is not the best point estimate for population standard deviation. Okay, basically for those mu and p that we did before, okay, we rely on limit central limit theorem, which says that the x bar will eventually get closer to mu, and the p hat will get closer to p as the sample size increases. Okay, so if we increase the sample size, then our sample mean will get closer to population mean, and our sample proportion will get closer to the actual population proportion. Unfortunately, that's not true for standard deviation. The standard deviation is not getting closer to population standard deviation, even when n is increasing. Okay. So central limit theorem does not apply to predict standard deviation. Okay. Now that's the reason. This is the reason most Ivy schools, most universities don't teach this until much later in statistics. If they ever, it will be much later. They usually don't teach that at 200 level. Okay, they have the word robustness. It is because the sample standard deviation is not robust. That's what it means, that even as n is increased, s may not getting closer to the actual population standard deviation. Okay, so it's very unstable, very unstable, and the requirement to use this method in this section is very strict. That is, the underlying population from which we get the sample from needs to have a normal distribution. Oh, hold on, Thomas. Something not really right. I really thought that we apply central limit theorem, and we apply central limit theorem when the underlying population has normal distribution. Not really true. Not really true. If you remember, central limit theorem actually says the following. It says that the first part is true, that if x is normally distributed, then x bar will be normally distributed. Okay, so if the underlying distribution is normal, then the sample mean will be normally distributed. But the second part doesn't require the underlying distribution to be normal. Okay, it requires that if the underlying distribution is unknown to be normally distributed, the sample mean will still be normally distributed as long as the sample size is at least 30. You remember that? So one way to apply the method we had earlier is either the underlying distribution is normal, or if the sample size is at least 30. Okay? That's for us to apply the model that we have earlier. Now, however, when we try to construct confidence interval for population variance, population standard deviation, we strictly require that the underlying population is normal. Okay, increasing the sample size does not make it approximately normal. In other words, simply because the underlying population is approximately normal is not enough. Okay, it has to be strictly normal. Okay, it's not only by the sample size. No, sample size. The problem with this model is you may increase the sample size and the sampling distribution get even further from the actual population standard deviation. Okay, so increasing the sample size does not solve our problem. Okay, what we need is the underlying population is strictly normal. Simply approximately normal is not enough. Simply symmetric or bell curve is not enough. Okay, simply the sample size is at least 30 is not enough. Now those are approximately normal or symmetric, at least 30 may work for mu and p when we try to find the confidence interval for mu and p, but not for this. Okay, so again, when you try to find how to construct confidence interval for sigma squared population variance, population standard deviation on YouTube, very likely you get the lecture videos coming from colleges, not from universities. And that's kind of strange. Like, you learn that in college, but they don't even use that in universities. Okay, that's because this model is very unstable, very unstable. Okay, very unstable. Now, but anyway, let me teach you how to do this. The procedure, because we don't have best point estimate, then procedure will not be the same to what we have in the past anymore. In the past, we have step 1, best point estimate, and then critical value, and then in step 2, we have margin of error. Step 3, then we have the confidence interval, right? Right now, it won't be like that anymore. Now, we still have 3 steps. I call that chi-square left and chi-square right, and then the confidence interval. Okay? Now, but what is chi-square left, chi-square right? Here's the thing. Chi-square distribution looks like this. Chi-square distribution looks like this. It's skewed to the right. It's not symmetric. Okay? Chi-square distribution is not symmetric, and it's skewed to the right. So it's supposed to, when I say skewed to the right, means it's supposed to look like this to make it symmetric. It's supposed to look like that to make it symmetric. But then the tail, the red tail here, you kind of push that to the right. It's kind of like stretched to the right. Okay. Now, second, chi-square distribution is a positive distribution. So the chi-square will always give you a positive number, never negative number. Okay, never negative number. It will always give you a positive number. Now, because of that, then when we compute the chi-square score, we have right tail, left tail. Now, right tail is the tail here, okay, such that the area to the right is what, and then left tail is here. This is chi-squared right, and this is chi-squared left. You know what? In my step 1, 2, I suppose I happen to write it in the wrong order. Supposed to be chi-squared right first, and then chi-squared left. Okay, now the idea of confidence level is still here. The confidence level is still the area in the middle. And then you divide by 2, the remaining by 2, that will be the area on the left and right tail. Okay, so this is the area on the left tail, and the area on the right tail will be the same. Now, how do we punch that chi-square left, chi-square right? Now, it depends. It really, you need to already program your inverse chi-square on your calculator. Okay, but let's start with an example. For example, this is finding chi-square right and chi-square left. Okay, suppose, let's say, for example, the alpha, no, not alpha, confidence level. Suppose confidence level is 95%. And then the n, let's say, is 25. The sample size is 25. Now then, suppose I sketch that chi-square distribution here. It means I want the area in the middle to be 95%. 95% here. And the area of each tail is 2.5%. This is my chi squared right, and this is my chi squared left. The way you write that chi actually looks like this. I enlarged that very big. Chi is like on the main diagonal, it looks like that. It's a curly, it's an italic capital X. However, by the other diagonal is a straight line, like that. And then you put a square there. Okay. Don't ask me why the person who first used this notation put a square. But I think the person who invented this notation tried to emphasize that chi squared has to be a positive number. Okay, or at least 0, but it's so hard to find a chi squared equals to 0. Okay, so if you know the Greek letter, this chi letter is the letter being used in Christianity. That's for Christ in Greek. In Greek, Christ, I think is Christos. Okay, well, don't worry about that though. No, it's not about that. But just in case you want to relate that to what the letters we use, okay? So that comes from uh, the letter chi. Okay? In our textbook, they write it as chi. Sounds like chi, but it's actually chi. The way you read it is chi. Okay, like so the word Christ, usually in the past, they use these two letters in Greek for Christ. Okay. Anyway, I want to emphasize that you need to write your chi notation that way. Now then, how do I then find a chi square right? Now chi square right will be computed this way. Unfortunately, I don't think I actually have that program here. Let me see. No, I don't have that program here. Have you programmed that on your calculator? I do. I have programmed that on my calculator. So, inverse chi. So I use the program inverse chi. Whatever you name your program is, okay. And then the area to the right. So you call the program area to the right. Is 0.025. And then degree of freedom is 25 minus 1. That's 0.4. Your calculator will take some time to compute it. And the result I get is chi squared right to be 39.36408. Now I want you to try it yourself. Do yours. Again, I assume you already programmed your calculator. Okay. I assume you already programmed your calculator. Chi squared right is when the area to the right is 0.025. Now, how about chi squared left? Chi squared left. So you call that program again. It's inverse chi. However, the area to the right is not 0.025. The area to the right will be the area to the right of that chi-square right left. Okay, so if the area to the left is 2.5%, then the area to the right will be 97.5%. Okay. So you will use 0.975. Degree of freedom still the same. Always sample size -1. So chi-squared left will be area to the right 0.975 and then degree of freedom 0.4. Your calculator will take some time for that to work. It may go even up to 30 seconds. So I get my chi-squared left will be 4.40115. Okay. Now, let me ask you to do this. Follow the
Thomas,
simulation.
can you
Yes.
demonstrate how do you do the calculation again with the TI-84?
You have to program that. You have to program that. Let's see, somewhere in the past, you have my discussion here, right? Okay, if we go back to last week's discussion, I believe I remind you guys to do this.
Okay.
Remember that?
Okay.
Okay,
I got it now. So I can.
Did you do that?
I haven't done that yet. I can
Yeah.
just look at the video and do it, I guess.
Yeah. Okay. Make sure you do it then. Okay. Should we do that together? Now the thing is, you know what? Let me give you like 5 minutes to look at that. I want you to do it though. I want you guys to do that. So let me click that one. Let me make sure that you have.
Wait, Thomas, can you show me how to do the inverse?
Give me a second.
Yeah.
Repeat again.
So so I did the program and I'm at the name right now, and how do you get to the inverse?
INV hi. Oh,
Yeah.
you type it one by one. So here on your calculator, you will see the I here. This is the I believe. So A, B, C, D, E, F, G, H, I. So when you type name, when you put the name in, it's already in alpha mode.
Okay. Which button do I click after I input the IMV Kai?
Go to the input.
The- Where's the input?
Program.
Okay, go to program again.
So from here, if you want to put that input, you press program.
Yeah, but in that case, I'm still in the alpha mode, I think. So
Yeah, after you name it, press enter.
okay, let me retry it.
After you put the name, press enter. And then after that, to get into that input, you will press program and then IO and then input. So to get to this input here, to get this input,
Mm-hmm.
you will press. Okay, let me press.
So how do you get input? I press program in this case, and
Okay, let's see it here. Okay, for you to get to that input, you press program. Okay, and then edit. Oops. I think I need to give it a name first. Okay, so name, create new. Okay, where's my N? In first high. Enter. Now then, we are here, right?
yes.
Now then, you press program.
Okay, program.
And then move the cursor to I/O. Input output. I/O. And then the first option is input. Enter.
Okay.
Yeah, that's where you get the input. Okay, and then actually let me do that input again. Okay, so that you see what we have in that input. In the I/O, you get input. That's what you need from there. And then for the control, I need to go up. Yeah, for the control, you have if, then, else, repeat, and whatever, while, and so on and so forth. Okay, and go to menu, program, and then the execute. It's that's the program. Okay, let me clear that here. So that's the input. Let's continue the video. The time is very strict, very close. So I may not let you finish this, but at least I show you how to do that.
Yeah, for sure. I think it's really helpful. Yeah. Wait, how was the area being input?
You just type it. Yeah, you just type it as letters. Yeah, so when you want to type that area right, including the quote unquote site. It's in alpha mode.
Okay.
Yeah. So if I go back to what we have there earlier here, okay. So I will do second alpha lock. That way, then it's I lock that as alpha, and then colon. The colon is here. Area. Where's my R?
Oh, so you plus math, then you plus alpha?
No. No, I actually use second alpha. You see above that, you see A lock.
Yes.
You basically lock the alphabet. Because if I put second only without alpha, okay, I'm actually getting the blue color, the matrix, sine inverse, cosine inverse, right? Okay, so if I want the alpha log, then I have second alpha, then start.
Yeah, but in this case, when I press R, I'm getting the X, not the actual R.
So very likely you didn't press the second earlier. So let me delete this first. So very likely what happened earlier was you have this, right? And then you press alpha R. Now, then mine is already locked in alpha. I don't know.
Yeah, I'm still trying to figure out.
Yeah, you need to lock that, not just pressing alpha, not just pressing alpha.
So I press second and alpha?
To lock the alphabet.
Okay.
Yeah,
I think it's working now. Yeah.
So let me go on area, and then space is here, right? Where's my R again? And then colon.
Sorry, I was. Which sign did you press for space in this case?
Above 0, that's the space.
Okay, gotcha.
Go back to that video. And then after this, I'm sorry. Before the colon, I need to put that. Before the code, closing quote, I need to put the colon. And then quote, and then comma, and then A. Go back here. I need to go back. This. I need the colon first. Where's my colon? I think the colon's here. And then closing quote. And then where's my comma? Not this one. I need to do that. And then comma, and then alpha A.
Wait, Thomas, can you show me where the comma is located?
The regular comma above 7.
7. Okay, that should. But I get J by pressing.
Yeah, but because you are still in the alpha mode, you need to get out from alpha mode by undo the alpha.
Okay, for sure. But then I press it again.
Yeah. So let me delete this and delete this.
And Thomas, do you know how to delete just like one syllables instead of hitting clear?
What I did is I go back and then press del to delete.
Yeah, sorry, I have a TI-84 plus, so my setting is a little.
No. Mine is also TI-84 plus.
So
we are the same. What I have here is also TI-84 plus.
Okay. So I unlock alpha. I press that again. Okay, I think I got it. Okay.
And then To get that A, letter A again, I go to alpha and then A.
Alpha A, yeah.
Now then, I go back to that video. Let's see what that comma that person used.
Oh, that's
Okay, let me give you some time to press it in. I do that too, so that we are on the same page,
yeah,
right?
for sure.
Okay, so I press enter here and then input. And then degree of freedom. So I lock the alpha mode.
Is there a
off.
space between input and the degree of freedom in this case?
Once you press input, they will do the space for you.
Okay, the space is automatic, yes.
And then DF, that's for degree of freedom, colon, close quote, comma. Now to get out from the alpha mode, I get out, comma, and then go back, call that D. So the quote unquote will be what appear on your what appear on your calculator later on, and you need to type in the numerical value for area to the right. Now the DF will be what appear on your calculator later on when they ask you DF, and when you key in the number, your calculator will take it as the number for the DF next to it. Okay, let's go back. We finish this up. The next thing is so how to get to that display solve. Display solve. So I'm here, press enter to go to display, program, IO, display. Boom. And then how about the solve? Solve, you go to math. I think, is it below here? Or numeric? Yeah, here. Math, and then go down pretty far, you get the solve. Okay, now we can continue the video. From here, I will press 1 minus. Now I will go to chi-square CDF. Second distribution chi-square CDF. Enter. So the lower value is what again? I think the lower value is x. Let's go back there. The lower value, oh, the lower value is 0. And then upper value is x, and then d.
For x, do we do the alpha x?
That's right. The letter x that you put in here earlier. So enter alpha x, alpha, where's my x? Here, and then enter. Degree freedom, at that time we use D, so letter D. Okay. And then I minus A as I remember. Oops, sorry.
Wait, Thomas, did you do alpha? Did you do alpha math for this case?
Alpha math for which one?
For A, okay, alpha. Okay, I think I got it. Okay.
Yeah, alpha for math because they have an A up that's for letter A. Okay, let's go back to this. Minus A and then x comma 0. Ooh. X comma 0. And then comma x, where's my x? Comma 0. I believe that's I think should be close parentheses. Yeah, close parentheses and then colon. Let me play that. Okay, let's start. Go back to my calculator. Did I close that already? Let me see. Did I close it? No, I didn't close it. Okay. Enter. Boom. Now then I'm done with the programming.
So did
Now,
you just hit enter?
Yeah, I press enter.
Okay.
After I close it with parentheses, I press enter. It gives me the new line. That's the colon. Now, to get out from here, I go to second mode. It's basically, I try to use the quit button. Now then, go back to the program.
Did you use the alpha parenthesis or did you just use the second parenthesis?
Do you have alpha parentheses?
Oh, actually, just the regular parentheses. I think.
Yeah. Now then, press enter, and that's the program in first chi. So to call that program, you go to program, and you have only one thing I program here. Okay, enter. Then what is the area to the right? Go back to my notes earlier. Area to the right for the first question is 0.025. So 0.025, enter. And what is the degree of freedom? 24.
24.
Boom. Now, if you see this notation here like this, it means your computer is running. The processor of that calculator is running. Okay, now I want to find the chi-squared left. which means the area to the right is 0.975. Degree of freedom, 24. That's how I get that. Okay, now then let me go back and finish up. So going back to my notes. I get these two values here. Then our step 3 will be, earlier I told you our step 1, step 2 is this. Our step 3 will be the confidence interval. So suppose my sample, so let me add here, so that's step 1, this is step 2. Suppose, for example, my sample standard deviation is 5.2. Then my confidence interval for population standard deviation is done. I need to do the sigma squared first. The formula is n minus 1 s squared over chi squared right less than sigma squared less than n minus 1 s squared over chi squared left. So you have the same formula except this. We will compute that. That will be 24 times 5.2 squared over 39 something. What's that? 39.36408 less than sigma squared less than 24 times 5.2 squared over 12.40115. Now then, after you finish computing that, then you go on with confidence interval for sigma. That is by applying square root to whatever number you get here. Applying square root to whatever number you have there, less than sigma, less than the square root of whatever number you have here.
Thomas, how did we calculate the area left in this case?
By looking at the area to the right, 97.5.
Oh, okay.
If the area to the left is 2.5%, then the area to the right must be 97.5.
Okay. Sure.
Okay. Time's up, so I will stop here. Your suggested homework will be from 7.5. So you go on yourself, okay? Suggested homework from 7.5 will be number 5, number 7, number 9, number 11, and then number 19. And number 21, hold on. That's for 7.5. Now, hypothesis test, your suggested homework will be, by the way, for that hypothesis test, we did a lot of examples already. You should be able to do from 8.3, do the word problems. Do number 9 to number 17. That should be good enough. Actually, start from number 7. We can start from number 7. Well, anyway, from number 9, 8.4.
Do we have a quiz for the week, or do we have a quiz for the week in this case?
No, just study from this. From 8.4, do number 9. To number 17 again. So 8.5. From number 9 to number 27. Just do this one, the odd ones. Okay. And I don't think I will give you any quiz anymore, like take-home quiz. I don't think so. I will, however, tell you that you can start studying from my old test already. So next week, what I will do next week is I will finish up 8.6 and then go on to chapter 9. That's what I will do next week. Okay, that's for today. We are over by 6 minutes because you didn't program it. Okay, you go program it and then work on this. Okay.